Hello friend, today we are going to learn the second application of Lagrange's equation, that is minimum surface of revolution. Minimum surface of revolution. First, we draw the diagram. Consider 2 points x1 and x2 and axis xy and z. That is x-axis, that is y-axis, and this is z-axis. Consider 2 points here, 1 point here, coordinate is x2, y2, and here 1 point, that is x1, y1 coordinate. The revolution are that is, and here and these 2 points and here the revolution is given by that diagram, that is draw x. Suppose we form the surface of revolution by taking some curve passing through two fixed endpoint, that is x1. This point is points of coordinate is x1, y1, and second point of coordinate is x2, y2, defining in xy plane. This is y-axis and this is x-axis, and define the plane xy plane. And revolution it about the y-axis, means revolution of that point about y-axis. Here y-axis and here also y-axis. The problem then is find to that the curve of which the surface area is minimum, means surface area of this curve is minimum. The area of this strip of the surface is, strip means this is a strip. Area of this surface strip of the surface is 2 pi x dx, and that is equal to 2 pi x, and value of dx, it is the shortest distance, that is 1 plus y dot square. It is calculate first example, means shortest distance between 2 points. And then the total area is 2 pi integral 1 to 2 x under root of 1 plus y dot square dx. And the extreme of this integral is again given by Lagrange's equation, where f is equal to x into under root of 1 plus y dot square, and then derivative with respect to x, that is del f upon del y, is equal to 0 because f does not contain y, and derivative with respect to y dash is del f upon del y dash is equal to x into the x is constant, and derivative of this 1 upon 2 under root of 1 plus y dot square, and derivative of y dot is 2y dot, and 2 cancel, and that value is x y dot upon under root of 1 plus y dot square. And in this equation, again derivative with respect to x means dx into x y dot upon 1 plus y dot square is equal to 0. from Lagrange's equation, this derivative is equal to 0, means x y dot upon under root of 1 plus y dot square is equal to constant, and that is a. Here a is some constant of integration. A is integration constant. Integration constant and smaller than the minimum value of x. This integration constant is smaller than value of x, and squaring above equation and factorize the term we have, means squaring this equation on both sides, then we get x square y dot square upon 1 plus y dot square into a square. Squaring the equation, squaring above equation, we get x square y dot square upon 1 plus y dot square is equal to a square. Then solving this equation, x square y dot square is equal to a square into 1 plus y dot square. Then again solve a square plus a square y dot square. Then take same term in one side, x square y dot square minus a square y dot square is equal to a square, and here y dot square is common. Then value is x square minus a square is equal to a square. On solving the means taking under root, then y dot into under root of x square minus a square is equal to a. Then you know y dot is equal to derivative of y with respect to x, means dy by dx is equal to a upon under root of x square minus a square. The general solution of this differential equation in light of the nature A is y is equal to a into integration of a dx, a take common, then dx upon under root of x square minus a square plus b, and then y is equal to a into integration of dx upon under root of x square minus a square. Formula is used, then value of this cos h x upon a plus b, and then value of x is equal to then find the value of x, that is equal to x is equal to a into cos h y minus b upon a, and which this equation x is equal to a into cos h y minus b upon a, which is the equation of catenary, and again the two constant of integration, that is a and b, are determined in the principle by the requirement that the curve pass through the two given endpoint. That is draw the figure, and that figure is given by x-axis. This is x-axis, this is y-axis, 2 point here, 1 point, that coordinate is x2 y2, and here again 1 point, here coordinate is x1 y1, and curve passing through this point is this curve passing through this point, and here in axis that value is b, constant b, and in x-axis that value is constant a. Means two given end point, and in this figure is figure 2. Curve satisfy the preceding preceding equation of all the scale at x by a and y by a with one independent parameter b upon a, and this suggests that when the solution are examined in detail, they turn out to be great deal more complicated than this consideration. And this suggests that for the some pair of endpoint, unique constant of integration a and b can be found, but other endpoint it is possible to draw two different catenary curves through the endpoint, and while additional cases no possible value can be found for a and b. In additional cases no found the value of a and b. Further recall, the Lagrange's equation represent the condition for finding the curve y of x continuous through the second derivative, and that render the integral stationary. The catenary solution therefore do not always represent the minimum value, but may represent the inflection point where the length of the curve is stationary but not minimum. For certain combination of the endpoint, the absolute minimum in the surface of the revolution is provided by the curve composed by of the straight line segment from the first endpoint parallel to x-axis and until the y-axis is reached. Then along the y-axis until the point 0, y2, and then out is a straight line to the second endpoint corresponding to the area pi into bracket x1 square plus x2 square, and this result when a is equal to 0, forcing either ax is equal to 0 or y is equal to constant, and says this curve has a discontinuous first derivative and we should not expect to find its solution to Lagrange's equation. This example is valuable in emphasizing the restriction that surround the derivative and meaning of the stationary condition. Then third example of Lagrange's equation is, that is the third example, that brachistochro problem. We draw the diagram, that is x-axis, that is y-axis, and 2 points are, this is 1 point and this is point 2, and line passing through this point, and velocity is v. This is the well-known problem, is to find the curve joining 2 points, that is 1 point and this is 2 point, along which the particle falling from the rest under the influence of gravity travel from higher to lower point in the least time, and if v is the velocity, v is the speed along this curve, and then time required to fall, and arc length ds is ds upon dv, means arc length ds, time required, the arc length ds, time required, arc length ds is equal to ds upon v, and problem is to find the minimum of minimum of the integral, that is time 1 to 2, time required from point 1 to 2 is equal to integral of 1 to 2 ds upon v. Means time required for the point 1 to 2 is integral 1 to 2 ds upon v. If y is measured down from the initial point of release, and the conservation theorem for the energy of the particle can be written as by conservation theorem 1 by 2 v square is equal to mg y. Then v square is equal to 2gy, and then v is equal to under root of 2gy. Then the expression for T12 becomes T12 is equal to integral 1 to 2 value of ds is equal to under root of 1 plus y dot square dx upon value of v is under root of 2gy, and f is defined, f is identified as f is equal to under root of 1 plus y dot square upon 2gy. The integration of Lagrangian equation with the form of f is straightforward and left as an exercise. The parametric solution in terms of parameter a is given by solution of the parametric solution in terms of the parameter a is given by x is equal to a into phi of phi minus sin phi, and y equal to a into 1 minus cos phi. And we draw the diagram for this point. We draw the diagram for this point is, that is y-axis, and that is x-axis. Here x, here y, and 2 point are this point, 1 point, this is 2 point, and that curve passing through this point is here, and here x2 less than equal to y2, here x2 greater than equal to y2, and that is pi a, and in this point x1 y1, and here in this point x2 is equal to pi by 2 y2, and this value is 2 pi a, and this is a, 2a, 3a. For the first cycle, 0, here 0 less than x less than 2 pi a. And the beginning of the second cycle, 3 cases of solution are indicated. A power series expansion of the solution for a limit y less than equal to a gives y is equal to a into cubic under root of n by 2 x upon a whole square. And the Brachistone problem is the famous in the history of mathematics, for it was the analysis of this problem by John Bernoulli, and that led to formal foundation of calculus of variation. And these are the two these are the 3 application of the Lagrange's equation. First is the shortest distance between 2 points, second is minimum surface of revolution, and third is the brachistochro problem. And this is the application. Thank you.